So now we want to discuss the coefficients of correlation and determination. So these are dealing with how good our linear model is. So the coefficient of correlation, sample coefficient of correlation, is given by the value r, and it's defined to be the sum of squares of xy over the square root of the sum of squares of xx times sum of squares of yy. So again, remember this is sort of the variation with x and y, the variation with x, and the variation with y. And then these are the same definitions that we had previously for those quantities. Now notice that r is going to be equal to 0 if beta 1 hat is 0. So if the slope of your regression line is 0, then your equation is just y hat equals beta 0. It's constant. It's a horizontal line. If r is close to 0, that's telling you that there is a little or no linear relationship between x and y. If r equals 0, it's definitely no linear relationship between x and y. If r is approximately 1 or negative 1, that is a high linear correlation. So it's a very strong correlation between x and y. So now just some examples here to kind of get used to the language. So if r was approximately 0.8, that would be a strong positive linear correlation. 0.5 would be considered moderate. 0.3 would be considered weak positive. And 0.1 or 0.2 would be little or no relationship. So there's really no hard and fast cutoffs here for weak, moderate, and strong. It varies on who you ask. So here's some pictures of what these mean graphically. So here's a scatter plot. We can tell that r is greater than 0 because our regression line will slope up from left to right. So it's going to be a positive correlation. As x increases, y increases. So if we were to sketch our least squares line, it would look something like this. And then here, there really is not a linear relationship there. This is going to be a case where r is really close to 0, little or no correlation, no relationship here between x and y. And then here you can see that the data channel down from left to right. That's the case where r is less than 0. There's a negative correlation. As x increases, your y decreases. And here, our regression line would look something like that. Slopes down from left to right. So r greater than 0, positive slope, r less than 0, negative slope. And then if r is equal to 1, that's a perfect positive correlation. So these points are exactly on the line. So your regression line goes through all of the data points when r is equal to 1. If r is equal to negative 1, that is a perfect negative linear correlation. So all your points are on the regression line, negative slope. And then here's a case where there is a definite relationship here, but your r is close to 0, no linear correlation, because there is little or no linear relationship between x and y. So there is a relationship, looks like a negative x squared curve, but it's not a linear relationship, and r only measures the strength of a linear relationship. Now, just a word of caution here, a high correlation here does not necessarily imply that there is a causal relationship between the two variables x and y. R just measures association. It doesn't measure cause and effect. So correlation measures association. We'd have to have a designed experiment where we're controlling x and controlling for confounding variables to show that we have a causal relationship. So let's look back at our example that we've been working with again here, where x is our medication dose in milligrams and y is our perceived pain level. So our relationship, regression relationship, was 8.478 minus 0.00861x. Sum of squares of x, y, and xy here we previously figured out. So our coefficient of correlation then, we'll have sum of squares of xy up on top, which is negative 2475. And in the denominator, we will divide by the square root of sum of squares of xx, so 287,500, times the 22.75, which is our sum of squares of yy. So let's go ahead and compute that on the calculator. So alpha y equal enter, give us a horizontal fraction in the numerator, 2475. Denominator, 2875. Oh, wait, we need to put a square root in there. So square root 287,500 times 22.75. So negative 0.967, negative 0.97. That is very close to negative 1. We would interpret this as a strong negative linear correlation. Actually, so it's so close to 1, most researchers would probably call that very strong negative linear correlation. Does this show that increased dose causes pain to decrease? No, it doesn't. It shows association. Now, it may well be that there is a cause and effect relationship, but correlation coefficient does not show that. Now, just to note here, the population coefficient of correlation, the symbol for that is rho. So the R that we figured is the point estimate for rho. And now, if we go back to our Jamovi output, you will see right there is our 0.97 R, our coefficient of determination. So what they're using, cap R, that's what we're calling little r. And if you look at the regression output here, so if we do stat, calc, and then linear regression for calculate, right there is our R, negative 0.967. So it's giving a negative value because we've got a negative slope. So now notice here that Jamovi did not attach a sign there.